Hello everybody. In section 17.1 we are going to learn about parametrized curves. And so what this means is, imagine you have a particle moving around in space. And over time you'd like to describe where that particle is. That's what we're going to do using parametrized curves. In the preliminary example, we're going to sketch our first space curve given parametrically. And so it's described as a vector valued function. We have r of t is equal to x of ti plus y of tj. So for each point in time, we have an x coordinate and we have a y coordinate. And we are looking at the time interval from 0 to 2 pi. Now, x of t is described by the expression minus 1 plus 3 cosine t, and y of t is described by 1 plus 3 sine t. And I mean, this is the first example that we're going to look at. We don't really know how this works. So a good idea first is to just plug in values for t and see what we can tell about the x and the y coordinates for these different values of t. So let's get started. What happens when t is equal to 0? Well, if t is equal to 0, we can look at x of 0 and get minus 1 plus 3 cosine of 0. Cosine of 0 is equal to 1. So this simplifies to minus 1 plus 3. So x of 0 is equal to 2. And I can enter that in my table. X of 0 is equal to 2. Now let's look at y of 0. Y of 0 is 1 plus 3 sine of 0. Sine of 0 is 0, so here we get 1. We can also put that into our table, and we can also write down the vector r of 0. That is 2i plus j, just writing it with our I and j components. Let's draw the points as we create them. This right here tells us where the particle is at time t equals 0. We have our x coordinate, we have our y coordinate. So at t equals 0, we are looking at the point x is equal to 2 and y is equal to 1. That's this point right there. And so this is where the particle is at t equals 0, and the vector r of t is the vector pointing from the origin to that point in the xy plane. So this vector right here is r of 0. We can now do this for all the values in our table, so let's just do one more. So what if t is equal to pi over 2? If t is equal to pi over 2, we have x of pi over 2, and that is minus 1 plus cosine of pi over 2. And when you figure that out, you get that this is minus 1. And then we can find y of pi over 2, and that is 1 plus 3 sine of pi over 2. And remembering that sine of pi over 2 is 1, we're getting 4. We can enter that in our table. So we have minus 1, 4, and the vector is minus I plus 4j. And we can also draw that in. So let's see, minus 1 plus 4 is up here. So this, sorry about that, this is the vector r of pi over 2, right there. And so you could pause the video and compute r of t and y of t, x of t, y of t, and r of t for pi, 3 pi over 2, and pi over 2 pi, and then start again and see if you were right. Okay, I hope you did that. I'm going to fill in the rest of the table. Okay, so for pi, our vector is minus 4i plus j. For 3 pi over 2, we get minus I minus 2j. And for 2 pi, we have 2i plus j. And I can also draw those points in our coordinate plane over on the right. So I already have the point 2, 1, the point minus 1, comma 4, then we have minus 4, 1, that is over here. Then we have minus 1, minus 2, that is down here. And then we have 2 and 1 again, which we already had before. I could fill in more of these, so I'm also going to draw in my 2 more vectors. So we have r of pi and r of 3 pi over 2. And then r of 2 pi is again where we started. It's the same as r of 0. If we computed more of these, we could convince ourselves that total we get a circle that is centered actually right here where the 2 is. You can't see that very well. So if I'm going to try to draw it, it's probably going to be awful. So it's a circle. Whoa, okay. Whoa, whoa, whoa. Well, imagine that was a nicer circle. So it's a perfectly round circle centered at minus 1, 1 and radius 1, 2, 3. That's what it looks like. Wow, that's a bad circle. Anyway, there's another way that we can convince ourselves that it's a circle. We can also look at x plus 1 squared plus y minus 1 squared. This is the circle that we think this is going to be. And if I plug in what x and y are equal to, so x is given as minus 1 plus 3 cosine t, and then plus 1, that whole thing squared, plus y is 1 plus 3 sine t, minus 1, that whole thing squared. When I cancel the minus 1 and the 1 right here, and the 1 and the minus 1, I have 9 cosine squared t plus 9 sine squared t. I can factor out the 9. Then I have cosine squared t plus sine squared t left. But cosine squared t plus sine squared t is equal to 1. And so we have 9 right here. So we really have confirmed that this is a circle of radius 3. So what is our particle doing? The particle that's moving according to the parametrized curves x of t equal to minus t plus 3 cosine t and y of t equal to 1 plus 3 sine t moves around in a circle. And we started over here at t equals 0 and then moved up to, let me change the color of my ink to show that a little bit better. So we are starting here and we are going over here. So we are moving counterclockwise.